Well, welcome to this video. It gives a short overview of the flat panel radome design and simulation software from rfhammer.com. Save the exe and the icon file to your PC and it should run on all standard Windows 10 machines. It might take a minute or two to open. It's a large number of files which have to be unbundled. The first window that opens is this one, where you can then select between flat panel radome simulation. This is this one. So there's one option over here where you can simulate flat panel radomes of an arbitrary number of panels, and where you input your own design, where you input the radome parameters. Or you can go to this selection where it actually does the design and simulation of the radome. So we have four options over here. We have a monolithic half wavelength design, A sandwich design, C sandwich design, and then a 7-layer sandwich design. Okay, let's first then have a look at the radome simulation. So we can click on that. And this window opens. We can run this. Right, so here we have the software for simulating flat panel radomes. So we have a number of windows over here. Over here we have the radome parameters which we can input. This one we have the plot parameters which we can input. And over here we have the simulated responses. So we have a frequency response and then an incident angle response. Okay, so in this case we have 5 panels which we're going to simulate. So each panel will then have a epsilon r, a dielectric constant, which we can input. It will have a tan delta, each panel, which we can input, and then the thickness of each panel we can also input. Right, so it will then simulate a radome with these parameters. Now obviously if you want to have 6 panels, you can make it 6, but then one is going to have to input values for the 6th panel. And if you want to simulate 1 panel, it will just ignore the values which are in the rest. So for 1 panel it's going to ignore the values of the 2, 3, 4 and 5 panels, and would only simulate then a 1 panel with these parameters. If we make that 2, it would simulate the first 2 panels. So you can make these 0 again if you want to, or you can just leave them as you are. It's up to you. Okay, so let's have a look at the plot parameters. So we can have a frequency and start and stop, so that will be on this axis over here. There's frequency start and frequency stop. We have a number of frequencies which you can increase if you want to, perhaps to make the marker a bit more accurate. We have a y-axis stop parameters, so for transmission. In this case it's set to -5. For reflection it's set to -50. So remember, you can also then simulate reflection over here. So in this case the y-axis is set to -50 dBs. So let's go back to transmission. So we have a frequency marker which we can move around, so we can make that 1 if we want to. More frequency marker will shift to 1. Okay, so it's shifted to 1. Let's go back to 10. Then it also has an incident angle, so you must remember that this plot is simulated for a specific incident angle. So in this case we have it at 20 degrees, but we can make it 0 degrees or anything between 0 and 90 if we want to. And as expected, the perpendicular and the parallel polarization values are now the same. So let's make that 40. We can run this. Okay, so remember we also have the 2 polarizations here. We have the parallel or the TM polarization and the perpendicular or the TE polarization. Okay, so on this side over here we have then the plot parameters for your incident angle response. Once again, we have angle start and angle stop, number of angles. Once again, we can change the y-axis for transmission and reflection. We have an angle marker. And then once again, this plot is dependent on a specific frequency, so we can input in that frequency. And once again, we can have reflection, transmission, reflection, or phase. So we have the phase as well. Then we get the phase of the frequency response and the phase of the incident angle response. Okay, so that was then. If you want to, if you already have a radome which you want to simulate, you can input your radome parameters here, number of panels, and then you can simulate it. So just remember that if you have 6 panels, and the 6 values over here have to be populated. If you have 1 panel, it will just ignore the rest. So if you have 11 panels, you would have to then input 11 parameters for epsilon r, tan delta, and the thickness. But if you want to then go back to 1 panel, you can just input the values for the 1 panel, and it will ignore any other values, panel values. Okay, so that was where you can do your own radome simulation. We input your own values. Okay, let's go to a design then. So in this case, we have then these 4 designs. Let's have a look at a half wavelength design. Once again, we can run that. So in this case, once again, with the radome parameters, which is going to be used in the design. So the epsilon r, the tan delta, the frequency, and the incident angle. Obviously, this design is then specifically designed in for these values. If we change the incident angle, we're going to get a different thickness. So over here we have the radome design, so it will give you the thickness of the panel. And once again, over here we have the responses, which are exactly the same as previously. And obviously, if you now make the frequency marker and the incident angle similar to the angle marker and the frequency, you're going to get the same values over here. But they don't have to be the same. You can input any values. And then once again, we can then simulate the reflection and we can simulate the phase. Okay, so that was then for a half wavelength monolithic half wavelength designer simulation. We can go to an A sandwich. A sandwich is where we have 3 layers, and where the 2 outer layers have the same dielectric constant, and the inner layer will have a lower dielectric constant. So usually this layer is a higher dielectric constant, and its skin thickness will be thinner than the middle layer, which is then a low epsilon r dielectric constant. Once again, we can specify frequency, and we can specify VSWR. Now, in this case, as for the previous case as well, for the half wavelength radome, we can play around with the thickness of the layers. If we make the frequency lower, and if we increase the VSWR, the thin layer, which is usually a problem in terms of its thickness, you don't want to get it too thin, will increase. So we can make this, for example, 2, and then this the first and the third layers thicknesses should increase. So we see they have increased slightly. And we can also look at the influence on the response. Usually, as we make the VSWR higher and higher, your insertion loss here is going to get more and more. So that is a trade-off you have to have. Obviously, we can make also the frequency lower. We can make this, for example, 6. And then we should see then also, obviously our response now is going to get worse at the higher frequencies. But we see that our thickness has increased. So you can play around with the VSWR and the frequency and to get a thickness value which is perhaps suitable for you, and then you can also see what the influence on the responses are. Okay, let's just have a look then at a C sandwich. A C sandwich has 5 layers. Okay, so 1, 2, 3, 4, 5. So once again, this program will design the radome for you based on your radome inputs and give you the thickness of the layers. Once again, the C sandwich radome has a thin high dielectric constant layer, and then the middle layers between the high constant dielectric constant layers is a low dielectric constant. These are the same, your plot parameters. Over here you can select specific VSWRs. This is basically based on distributed low-pass filter prototypes. You can refer to the references in rfhammer.com. But once again, if we make the frequency lower and we increase the VSWR, you can then increase the thickness of your high epsilon R layers, which is perhaps what you want. In this case, we have now 1.5 millimeter thickness, which is perhaps more suitable to make. But obviously, then your insertion loss is going to increase. So that's a trade-off you have to consider. But it's nice in the sense that you can then play around a bit and get a design which you want. Obviously, once again, this is for a specific incident angle, your frequency response. So there we have now a different frequency response for that incident angle. You can see the perpendicular and the parallel polarization case, and once again for your incident angle, you can then also play around with your frequency, and then you can change your angle marker as well. Okay, so that was for your C sandwich. We also have a 7-layer multi-layer design where you have, in this case, 7 layers. Once again, everything's the same except you can have 7 layers. In fact, with using the low-pass distributed filter prototypes, we can go up to these tables. The tables go up to many layers. But I've just, in this case, restricted it to 7 layers. I don't know if one really wants to make a radome with more than 7 layers, but if you do, just let me know and I can upgrade this. Okay, so there we have the different options which we've considered. It's a nice program. You can play around with the input parameters. You can adjust your thicknesses by varying your frequency and your VSWR, and each time you can see your response. So if you want a response to a certain frequency, you can then adjust your frequency and you can see what the response, the frequency response is, and then also you can also see what the incident angle response is like. So it's nice to see those together, and it helps with your radome designs. Right, thank you for watching this video. Trust it was informative, and remember to visit rfhammer.com.